Hello again. We're continuing our discussion of ceramics, and before I mentioned that one of the important ways in which ceramics were different from other classes of materials is that they are brittle rather than being ductile. And so over the next few sessions we will discuss our second major topic about ceramics, which is how do we accommodate the brittleness of ceramics in our designs of the way that we use them, and how do we try to come up with new ceramics or combinations of ceramic materials to overcome the brittleness and make the ceramic products stronger and make them last longer and make the length of their lifetime more predictable. So to give you an idea of what we mean when we say that ceramics are brittle, when we apply a force to a ceramic material and try to get it to move, it usually doesn't move much at all. If it does move, then all of the movement is elastic deformation. None of it is plastic or permanent deformation. If we relieve the force, then the ceramic material will snap back to its original size and shape, relieving the elastic deformation. Another way of saying that in materials terms is that if you deform a piece of ceramic until it breaks, then it breaks at 0% elongation, whereas metals, for example, will typically have some percent of elongation that remains after they fracture. So just how brittle are ceramics? If you look at the graph here, fracture toughness is on the y-axis, and a lack of fracture toughness is brittleness. So brittleness is inversely related to fracture toughness. So the brittle materials, the natural tooth and the ceramic, are down here on the bottom of the toughness axis. And we see that although metals and polymers span quite a range of toughness values, that ceramics have a narrow range with very low toughness. And I have to mention that I have not included all metallic materials, not even all metals used in dentistry. For example, there is dental amalgam, which would come in here at around 10. And I've chosen to leave that out because we don't use amalgam in applications where the toughness is an important consideration, like we do with other metals and with ceramics. And so the ceramics have an upper toughness of the toughest ceramic material we have is reported in the literature to have a toughness between 8 and 15, depending on the publication. I tend to think that the values above 8 are usually because a faulty method was used to measure the toughness of this material. So we can say the toughest ceramic has a toughness of 8. Most ceramics have a much lower toughness, in the range of 0.7 to 1. It's typical for the bottom of the scale, and most ceramics are on the bottom of that scale. And so we're talking about very brittle materials. Even the toughest ceramic material at 8 would be less tough than dental amalgam, sitting here at 10. And polymers span this wide range, and that's because, in part, the temperature at which polymers behave brittle or ductile spans a wide range. So with polymers, they can have temperatures in which they change their behavior at much lower temperatures than ceramics and metals. And we'll cover that in more detail with other faculty when you study the polymer section of the course later, though. Okay, so what does it mean to have a material you're working with that's very brittle? What it means is that the strength of the material is going to be sensitive to the presence of flaws. Examples of flaws would be pores or inclusions inside the microstructure, scratches on the surface of the material. And since the strength is sensitive to the presence of these flaws, that means, as we mentioned before, that the actual strength of ceramics in the practical world is much, much lower, 1,000 times lower than their theoretical strength. Theoretically, ceramics have, and this we're talking about failure stress or strength of the material now instead of toughness on the y-axis. That's strength on the y-axis. The theoretical strength of ceramic materials is higher than all other classes of materials. However, because there's sensitivity to the presence of these flaws, and these flaws are always present to some extent in all materials, and so the actual strength of most ceramics in use is down here in the lower range. And also because the severity of the flaws from one piece of ceramic to another piece of ceramic is variable, and the strength is very sensitive to the severity of those flaws. That means the strength is going to be quite variable, and the amount of time that a ceramic component lasts before it breaks is going to be quite variable, very difficult to predict. So that's a problem with ceramics that we have to figure out how to overcome. And we have 3 methods for overcoming this low strength and low predictability of strength or lifetime. The first of those methods is flaw reduction. By processing the ceramics, getting them into the shape we want them in the proper way, we can reduce the number of flaws they have in them. We can reduce the severity of the flaws that are there. And by treating ceramics carefully after we finish shaping them, we can avoid introducing many additional flaws, and that will result in their strength being higher. However, this isn't the best method to use, because after a ceramic part goes out to be used, for example, is placed in the mouth of a patient, additional damage can accrue to the component, and then the strength will be reduced. So the flaw reduction method of increasing strength only helps the strength at the beginning of the lifetime of the product. Another method, another strategy, is to put obstacles in the microstructure that will prevent any flaws in the material from growing larger and causing the material to break. And so these are obstacles to crack growth. And this has the advantage that if we have any flaws that are in the material from the very beginning, it will oppose their growth, and if any new flaws are introduced later, it will oppose their growth. So it makes the ceramic tend to stay strong throughout its lifetime. However, those flaws can still grow somewhat over time, and so another method of dealing with the brittleness is to put a compressive stress in the ceramic that will push cracks closed when they try to open up and grow through the material. And this method is quite effective, but it can only be applied to some types of ceramics. Unfortunately, not all types of ceramics, and it can't be applied to the strongest ceramics that we have. Only the weakest ceramics can take advantage of residual stress. And so next I'll tell you a little bit more about each of these methods and how they're accomplished. But first, before we can do that, I have to educate you in fracture mechanics, and we'll have to learn some definitions of how we characterize the flaws and how we characterize the forces and stresses that these materials must withstand to have a long lifetime. So if you consider that we have a rod of ceramic material here, and this rod has a force placed on it, we're pulling on either end away from the center, and that force is going to cause a stress everywhere in the rod of ceramic material, and the stress that it feels, when that goes past a critical level, then the material will break. And that critical level of stress, the failure stress that a piece of ceramic can withstand, is also the strength of the material. So you may hear me refer to failure stress, or sometimes to strength. Those are the same things. And the units of stress are units of pressure, megapascals. And a pressure is a force acting over an area. And if we divide the amount of force that we're pulling on the ceramic with by the cross-sectional area that's distributed over, that will give us the stress that the ceramic component feels everywhere in it. And however, as we already discussed, the surface of all objects are covered in small flaws. The interior has some flaws in them also, scratches, pores. If we take a closer look at one of those flaws on the surface, this is a scratch in the surface of the material, and we will see that that sharp tip on the scratch concentrates the stress only near the tip of the crack or sharp scratch. So far away from that flaw, we find what we call the far field stress, the stress that we would calculate according to this equation. And as we approach the tip of that flaw, the stress increases as we get closer to the tip. If we get into this range, whether it will level off or not depends on whether you have a material where the tip of the crack remains sharp, or whether it can be blunted by the material. And another way that we talk about the point at which materials fail is to talk about the stress intensity factor. Stress intensity factor is similar to stress, but it includes some other important factors in addition to the stress, such as the size of the flaws that the stress is acting on and how sharp those flaws are. And so if we take the far field stress and we multiply it by the square root of A, where A is the size of the flaw in question, and we also multiply that by Y, where Y is a factor that includes aspects such as how sharp the crack is. Y would be higher for a sharp crack than for a blunt crack. If we multiply all three of those factors together, we get K1. This is a Roman numeral 1. K sub 1 is the stress intensity factor, and it has units similar to the units of stress, but not exactly the same. At a critical level of stress intensity factor, the material fractures. And that critical level is known as the fracture toughness. And so when we talk about how tough a material is, we're talking about how high the stress intensity factor can get before the product fails.